of something I'll talk about in a moment, the case of 9 points in P2, a case of 9 points in P2, I should say. You may notice we've gone from 4, and then if you went to Jessica's talk, to 5, now 9. Perhaps there's some sort of additivity implicit in this process. But think where we could get if we went on another week. In any case, there are various different possible ideals and situations for 9 points. I do not want to exhaustively list all of them. If you do all the exercises in my book, you'll get to do that yourself. But the most obvious way to get 9 points is to intersect two cubics. A complete intersection of two cubics by Bezout's theorem is, of course, 9 points, and it has a rather simple resolution. It's a Koszul complex. I won't write that down. In general, of course, if 9 points are general in the plane, they impose 9 independent conditions on cubics. There is a 10-dimensional family of cubics, so you only expect one cubic through 9 points. It's a kind of accident for there to be a second one. The general way that accident happens is there's a complete intersection, but it can be more special than that. And you could have two cubics which, however, fail to generate the ideal. So I want to look at the special situation, which is guaranteed by the existence of which is guaranteed in any case by the general theorems that Rebecca talked about yesterday. Jessica, I'm sorry, talked about yesterday. For some reason, those two names are close in my mind. And that's the situation where the ideal is generated by two cubics and a quartic. And the only way that can happen is for the two cubics to have a common component. Otherwise, of course, they would be a complete intersection. I want to focus on the case when the common component is a quadric, a conic. That's what happens here. So let me draw a little picture of this conic. And the two cubics are made by taking a line and the conic, or a different line and the same conic. And then there's a quartic, and the 9 points are going to be the 8 intersections of the quartic with this conic and this point, which will also be a point in the quartic. So I'll draw the quartic like this. That's a sort of vaguely quartic curve. So what does the resolution of such a thing look like? Well, turns out that, of course, let's look at the homogeneous coordinate ring. So this is x, and then a resolution would look like Sx. S, of course, maps onto that. I have two cubics and a quartic. So the two cubics are represented by cubic generators of the ideal. I have to map free modules of generator degree 3 onto them, two of those, and one with generator degree 4, that's the quartic. And then I want to look at the situation where there is, well, this situation, in fact, where the two cubics, since they share a common quadric, they'll look like L1 times Q and L2 times Q, and the syzygy will be L2 times the first minus L1 times the second, so there'll be a linear syzygy on these two. So I'll see an S of minus 4 here. And then there'll be one more syzygy, as it turns out, of degree 6. Total degree 6, like that. And that's the end of the resolution. So you have to trust me that there is a resolution like that. As I say, it's guaranteed by the things that Jessica said yesterday. And now how do we write down the Betty diagram in this picture? So here's the degrees, 0, 1, 2, 3, 4, I guess. I have one generator, that's this generator over here. Remember, the Betty diagram is written in backwards order. That's perverse, isn't it? I really should just turn it around. But somehow all the accumulated experience with the program Macaulay would annoy the people who've used that if I did that. I could turn the resolution around. That's what, of course, the Macaulay people were hoping I would do. Somehow I can't bring myself to do that either. Anyway, there are no linear relations, no quadratic relations, 2 cubic relations, and 1 quartic relation on this generator. And then there's 1 linear relation between these two cubics, and no quadratic relations at all, and 1 sextic relation here. So this 1 is the sextic. Okay, so that's the picture of the resolution, the numerical picture of the resolution.
Can you remind us how the diagram corresponds to this?
Sure. So this that corresponds by columns. This column corresponds to the S. Sorry that the things are small. S. This middle column corresponds to this middle module. And this last column corresponds to this column here. And for example, this 1 represents a generator of a free module in degree 2 plus 1 plus 1. In other words, 4. It represents this generator. This 1 represents something in degree 4. That would be here. 5, 6. That's this generator. Okay? So in general, something in the ith row, j steps back, represents a generator of the jth module in degree I plus j. So there's the column. We'll come back to this example in a moment. Now, I wanted to talk a little bit about what would have been the end of my talk yesterday if it had gone on an hour and a half, and tell you some open problems about free resolutions in the general sense before we come to what will be the main topic for today, which is the study of what I'll call the linear strand of a resolution. We'll come back to that. So, what would you like to know about resolutions? Well, first sort of obvious thing is, how big are they, in some sense? Well, how long are they, for instance? So, how many terms are there in the free resolution? This counts as a resolution of length 2. This is F0, F1, F2. And in general, of course, the good answer is given by the Auslander-Buchsbaum formula. So the projective dimension of M is the dimension of the ring, which in our case is R plus 1. Remember, S is the polynomial ring in R plus 1 variables, minus the depth of M, if you like, the depth of the maximal ideal, homogeneous maximal ideal on M. That's a pretty good formula. It certainly tells us the range. Hilbert's theorem already told us how long a resolution could be. You could try to refine this various ways with estimates, but I don't want to do that. You might ask for a different kind of information, somehow in terms of these matrices. How long? Suppose I just write down a matrix. How long do you expect the resolution will be? Well, you might try to compute the depth of the cokernel. Actually, the fastest way to do it is just to compute a resolution, see how long it is, and use that formula in reverse. But there are actually other ways of doing it, and in some sense, there's a good description of how long to expect the resolution to be, which is also a proof of the Hilbert-Syzygy theorem by Schreier in terms of initial ideals. So there are various things you could add to this picture, but I don't want to go down that route so much. And the second question is, if you think about this in terms of Betty diagrams, I guess I should say how high is the Betty diagram? And there, Jessica talked about a description of that. That's called the regularity of the module. Now, giving it a name is nice. Of course, that doesn't tell us what it is. You might ask questions about how high it could be, just like we asked in the case of the Hilbert-Syzygy theorem, how long the resolution could be. That's the crudest question. The answers here are very interesting and very much a focus of active current research. So let me tell you a little bit about what's known and what my favorite conjectures in this direction are. If you ask a bunch of experts about this, they all have different favorite conjectures because there are lots of different kinds of things you might hope to say about it. First of all, in terms of what could we possibly ask this question? It turns out the natural, or the most primitive way to ask it is in terms of the number of variables. So remember, we're in S, which is polynomial ring in R plus 1 variables. And M, well, we need some information about M in order to bound this. Obviously, you can't bound it for all M, because if you just take ideals with generators of degree 1,000,000, then the regularity will be at least 1,000,000. So there's nothing to be said. But maybe if M is an ideal and you bound the degrees of the generators, that would be a reasonable thing to do. So let's take M, an ideal, whose generators are of degree less than or equal to D. So that's the kind of thing you might choose. Now, let me look at a special case first where this is a number that everybody has played with and where it's really easy to understand what's going on, and there's a beautiful, simple picture, quite misleading actually for the general case, but nevertheless interesting. So, case A, suppose M in S is primary to the maximal ideal x0 up to xr, which remember I've called script M. So big M is script M primary. In other words, contains a power of big M. And then the regularity. There's always a question whether I mean the regularity of M as a module or the regularity of S mod M, and that makes a difference of 1. So I'm going to ignore that difference. But the regularity of M is then equal to the smallest power of the maximal ideal that M contains. Smallest T, such that M contains the lambda to the T. So that's pretty simple. And one of the things that's nice is that if M contains M prime, then the regularity of M prime is obviously bigger than or equal to the regularity of M. Or put it differently, suppose I just know that M contains each of the variables to the dth power, then by estimating which power of the maximal ideal lies in the ideal generated by the dth powers of the variables, I get a bound on the regularity. So a corollary of this is, in this case, if M contains a regular sequence of degrees A0 up to AR, then I just have to look what the regularity of that ideal generated by the regular sequence is, and that's a bound for the regularity of M. So the regularity of M is less than or equal to, and you probably all can think this one through as well from your seats as I can up here. If these were the powers of the variables, then the last element not in the ideal would be the product of one smaller powers of the variables. So that plus 1 is the first power of the maximum ideal that's in, and the regularity is less than or equal to 1 plus the sum of ai minus 1. Right? So that's the kind of nice formula that it holds in this case. Now, in the most general case, we have also bounds, and they're pretty weird. The regularity of I. So, if, by the way, if m, sorry. So again, m is in S, generated in degree less than or equal to d. That's my hypothesis. It's on the board behind there. Here, of course, if I were in the primary case, I could take all the AIs equal to d, at least over an infinite field, and that's a harmless assumption here. So I would have a nice linear bound in terms of d and r for the regularity. But in general, the best that the world knows how to do is to say that the regularity of m is less than or equal to twice d to the power 2 to the r minus 1. So something pretty awful. This is due essentially to Greta Hermann long ago. And so you say, well, you know, how could such a nonsensical bound really represent the truth given that example? However, there's a famous example due to Meyer and Weyer-Stillman in the Syzygy case, which says, so there exists M with d equal to 4, where the regularity of M is at least, I don't think it's known exactly, 2 to the 2 to the r minus 1, no, sorry, to the r plus 1, plus 1. So, pretty close to the worst possible situation in some sense. Now, what I didn't tell you is how large this example is. To play this game, you need 10 times r plus 1 variables, and you need 10n minus 5, 10n minus 6 generators. So that to get anything, sorry. This r is different than this r. That's my problem. Phooey. So I guess this should be r plus 1 over 10. There's a number n in the original computation, which is this one. So n is r plus 1 over 10. Sorry. So this is r plus 1 minus 6, or thereabouts. Anyhow, to get an actual large regularity out of this, you need a lot of variables. So I think a good question that somehow no one has succeeded in is to find some examples with high regularity which actually have few enough variables that we can look at them. So Craig Hunicke and I spent some effort on this a few years ago. G. Co. carried that project through and has examples of this general ilk where d equals 2, but I think there are even more variables and equations. So we still don't have a satisfactory family of examples which achieve this kind of doubly exponential bound. So this would be a very, very valuable service to the world to produce examples with high regularity. Yes?
That's only r minus 5
Yes. This is not a primary example. It's a fairly low codimension example. Everyone seems to believe that the trouble comes from an embedded component at the origin, which is really nasty, or an embedded component somewhere. But really nobody understands this example from an algebraic point of view. It's well beyond the reach of computation by the time you get up to some reasonable value for n, and we're in the dark. That's all I can say. So I hope somebody will someday find a better family of examples to play with. This example is extremely clever and really resists modification quite strongly. Now, however, that doesn't mean we should give up on principles like this. And I think the following is a plausible conjecture. Rob Lazarsfeld told me it was his favorite conjecture of this kind. So, conjecture, I don't know to whom to attribute this, possibly Lazarsfeld. If M is a prime ideal, and I guess I better assume K is algebraically closed, then that kind of principle still works. If M contains a regular sequence with degrees AI, then the regularity of M is bounded by basically the sum of the AIs. A regular sequence of length equal to the codimension of M with degrees A sub I, then the regularity of M is bounded by the summation of whatever is written up there, 1 plus the summation of the AI minus 1s. No one will complain if you just prove that it's the summation of the AIs. And this conjecture is made plausible by the following theorem of Ein, Lazarsfeld, and somebody else. Who am I forgetting? Peskin. Sorry? Bertram. Yeah. So, Bertram, Ein, and Lazarsfeld. This is okay in characteristic 0 if the variety the projective variety represented by M is smooth. If M, let's say V of M, in projective space is smooth. And the proof is actually quite simple. So, but it depends on all these vanishing theorems. So you need smooth spaces, you need characteristic 0, probably all irrelevant. Maybe tight closure can come to the rescue. Do something.
Homogeneous in that case?
Everything is homogeneous. Sorry, I've said that yesterday, but I guess I forgot to say it again today. Regularity, as I've defined it, these graded resolutions, graded Betty diagrams, only make sense for homogeneous ideals. You could take associated graded ideals and do something, but this is the real case. So that's pretty good conjecture, and would give us a beautiful situation where primeness somehow plays a major role. So we have to understand what the interaction of primeness and regularity is, and nobody knows how to do that.
David?
Yeah.
Counterexamples to this kind of conjecture when M is primary?
Sorry?
When M is primary, are there counterexamples to this kind
It's true. It's true and trivial. There's, primary to the max. Sorry. Not that I know of. In fact, there's a great paucity of real bad examples in this area. I think there are examples of, in fact, I know there are examples of pairs of ideals where one is the radical of the other, maybe, and the radical has worse regularity. That kind of thing can happen. But this is a plausible conjecture for many ideals. Yeah?
Do you or maybe anybody in the room have an example where it goes not doubly exponentially, but exponentially?
So
in between these.
An example where it grows exponentially, of course, doesn't make any sense. But so I think this is a sub-question of what I said. We don't know enough examples. We just don't have families of examples which exhibit the kinds of behavior allowed by this horrible dichotomy. Let's see. We could go further than this. You might say, once you're talking about prime ideals, it's completely silly to work with the degrees of the generators. The natural measure is the degree of the projective variety, not the degrees of the generators. So what about that? And there's several nice results. It's easy to check from essentially what's written here that in the Cohen-Macaulay case, the regularity is bounded by the degree, in fact, a little better than that. And so you might say, well, that's a special, just reducing to the primary case again. But in fact, for two-dimensional prime ideals, one-dimensional trivially and two-dimensional prime ideals not at all trivially, it's known that the best possible kind of thing is true. So, theorem, the earliest version for smooth curves in projective space was proved by Castelnuovo, I guess in P3. And by Gruson, Lazarsfeld, Peskin a few years ago in general. So if P is a two-dimensional prime ideal, then the regularity of P, this is now over any, I guess I need algebraically closed or an absolutely irreducible prime, but any characteristic will do. Then the regularity of P is bounded by the degree of P minus R plus 2. Let's see if I got this right. So for the twisted cubic in P3 is an example which is sharp. So the degree there is 3. R is 3. The ideal is generated by quadrics and has a linear resolution. So the regularity is exactly 2. And this is the right formula. Now, if you think about the Cohen-Macaulay case, then you see that this fits right in with the best possible statement in the Cohen-Macaulay case. And so you might conjecture that the corresponding theorem is true in general. And this was written down by myself and Goto. But I think other people probably thought of it too.
See, what is R here again?
R is the ambient dimension. So we're in R plus 1 variables. We're in PR. So this is a curve in PR, right? That's what this theorem is about. If you want to read a proof of this theorem, then you can find one from a sort of algebraic point of view in my book on the web now. I just posted the most recent version last night. And, of course, the geometric proof, nice paper of Gruson, Lazarsfeld, Peskin, about 15 years ago. So the conjecture is that, in general, P prime, again, in the homogeneous situation, again with algebraically closed field, implies that the regularity of P is bounded by the degree of P minus the codimension of P plus 1. So that formula comes out to this in the case of curves. And again, nobody would sue you if you proved this with just the degree of P, for example. Now, why stick with prime ideals? How about reduced ideals? This kind of thing is false there, but it might well be true with the degree. If you took an equidimensional reduced ideal, and there's a recent theorem of Dirksen and Sidman along this line, that if P is the, or M, let's say, the ideal of a union of planes in PR. Planes of different sizes, different dimensions, any dimensions you like. They can meet any way you like. They can fail to meet any way you like. Then the regularity of M is bounded by the degree of M. And that's best possible in this case. So one should believe that for nice ideals, maybe reduced is what nice means, maybe primary is what nice means. Who knows what the right condition is? For nice ideals, there should be very much better theorems than this one, and we basically don't know them. Yeah?
So when you say degree of M, are you counting only the highest?
No, I'm sorry. The sum of the degrees of the components of M. The number of components. Yes, sorry. But it's like the degree. It's one possible interpretation, though the wrong one for the degree. So those are some positive results in that direction. And by the way, this conjecture has been checked in slightly less strong forms. It's known, I should say, it's known by a theorem of Mumford that if P is prime, then the regularity of P is bounded by essentially by a linear multiple of the degree. R plus 1 times the degree plus a constant, something like that, is true in general. So there's no trouble like the exponential trouble over there. I guess that's just in characteristic 0. That actually follows from this theorem of Lazarsfeld and company. Smooth, yes, thank you, smooth. And it's known from work of Peyeva and Sturmfels that such things, I think this formula itself is true for codimension 2 toric varieties. Have I got it exactly right? So, and it's known that it's true for Buchsbaum surfaces, I think. And there are various funny little classes for which people have been able to check this. For smooth surfaces in Pn, I think this is known to be true on the nose, or it's up to 1 anyway, up to a constant. This is known to be true. It's known to be true up to a constant, up to smooth fourfolds, I think, by work of Kwok. And his work also refines Mumford's work up to dimension 14, at which point it breaks down completely. So it's a messy and very partial picture that we have of this. And I think it's a great field for endeavor for, well, maybe somebody younger than I am, let's say. All right, let's see if there's anything I missed here.
Could you remind us how the regularity fits in with the height of the Betty diagram?
So the regularity in this picture is the regularity of the ideal is the number of rows in this diagram.
That you need to go all the way down to the 1.
To go down to the 1, right. So, right. So here it would be 5. There are 5 rows.
And that has to do with the S minus 6.
Right. This is, 4 should be the regularity of Sx, and 5 the regularity of I in this case. Because this is, for I, this is F0 and this is F1, so we have to take 6 minus 1. That's what contributes to regularity. Right.
But it has to do with that S minus 6.
Right. Maybe I should write down the definition of regularity again. I guess I said it, that it was the height of the diagram before. But in general, not the way it's usually defined. There are several choices for the way it's usually defined. I think it's time to start erasing. I don't want to erase my example. And this is a mistake. So I guess for those who neither knew the definition nor went to Jessica's talk to find it out, I should have said at the beginning that if I have a modulo M and the resolution F0 up to F something or other T, and if the Fi is the direct sum of S of minus Aij, some j, then the regularity, this is a minimal resolution, and the regularity of M was by definition the maximum number among Aij minus I. So in the case of the ideal, here, for example, the resolution would begin with this s minus 3 squared plus s minus 4. That would be f0. This would be f1. So I'd take 3 minus 0, 4 minus 0, 4 minus 1, and 6 minus 1, and take the maximum, which would be 5. There are cohomological definitions, and those were indeed the original ones, but this is the one that's closest to this set of lectures. There are other kinds of questions you could ask about the size of resolutions. For example, the syzygies in a resolution are torsion-free modules. They have ranks. How big would the rank be? And there's a famous theorem of Evans and Griffiths that says that the rank of an ith syzygy, unless it's free, has to be at least I. Probably much more should be true if you have a resolution, for instance, of a module of finite length. Then Buchsbaum and I and Horrocks all conjectured long ago that the rank would be at least a binomial coefficient. I guess the number of variables choose the number of variables minus 1 choose I minus 1 is, I think, the way it comes out. But whatever it is, it's the number which actually happens in the Cazul complex in the resolution of the residue field. And a corollary of that would be that the sum of the Betti numbers would be at least 2 to the number of variables for any resolution of a module of finite length. That conjecture has resurfaced recently as a conjecture in topology, slightly generalized, of course, which has to do with actions of groups on wedges of spheres. So, sorry? Products of spheres. Sorry. So, work of Gunnar Carlson, I guess, is the right reference for that. So there's lots of interest in such questions, and as far as I know, basically no progress in answering them. So I don't want to go on talking about that, but rather I want to turn, unless there are questions about these things or discussion of other impossible questions or easy questions, I want to turn to the linear strand of a resolution. Any point? One want to raise any question? Yes, Jan.
Conjecture about the finite length modules.
So the conjecture about the finite, the question was, where is this conjecture about the finite length modules? Oh dear, this is a long time ago.
It appears in a paper of mine called Open Questions in Topology. In the Journal of Topology.
The sum of the syzygies being the...
No, the one about the rank of
the rank being... So, and when is that?
Oh, it was a conference Tia had at Cambridge a long time ago. It's about 1980.
So there's a Robbins paper in 1980.
Problem list. Problem list
and you attribute it to Horrocks there, or to Horrocks? Buchsbaum and I published this conjecture in about 74. I think Horrocks' reference is about the same time. And I don't remember which paper it's in, to be honest. Yes?
The reference to that paper in your book.
Ah, so there you are. Someone has read my book. That's nice. Yes. In the paper on structure of codimension 3 Gorenstein rings. Lucio reminds me. Thank you.
One thing you mentioned, is the practical things about regularity that for us who were born before computers were.
Yes.
But it has to do with the stopping of.
That's right. So if you actually want to compute Grosvenor bases or compute resolutions, then you better hope that the regularity is linear rather than doubly exponential. In fact, if the worst case were always fulfilled, then we would have none of these programs like Macaulay and Cocoa and Singular. They wouldn't do anything.
Or else if anybody started them, they'd still be running.
That's right. They'd still be running. We'd never have found out the free resolution of the twisted cubic. So, but fortunately, they don't seem to be satisfied for geometrically interesting examples which seem to behave much better. But basically, the regularity is the best complexity measure for this process that we have. So it's of great practical importance in computation. Okay. Yeah, please.
This seems to be connected to injections of chromatic polynomials, like coefficients, size of the coefficients, and so on.
Now, chromatic polynomials appear as Hilbert functions often. So the question was, is this, I guess it was not a question, but an assertion, that, is this connected to chromatic polynomials? So I've seen chromatic polynomials connected to Hilbert functions of things. Dave Beyer is really one of the world's experts on this question, and he's around this semester, although not in this room. So we should find him and ask him this question, because he will tell you a lot of interesting things about it. But I'm not really an expert. Okay, so let's press on. We have a long way to go, actually, if we are to get where I hoped we would get. And talk about the linear strand of a resolution. So let's think about a general minimal free resolution of a graded module again. I'm going to talk about the linear strand. So M, again, is a finitely generated, graded module over S, which is this polynomial ring in R plus 1 variables. And it has some free resolution. I'm, just to simplify the notation a little bit, I'm going to normalize things and shift the degrees so that the smallest degree generator of M is in degree 0. So if you start with an ideal, and we'll be interested in this ideal in a moment, this ideal I would have to shift 3 degrees up to make its first generator in degree 0 before applying the things here in the form that I'm going to write them down. But you could imagine working with modules generated in any degree if you prefer. So I'm going to assume that M equals M0 plus M1 plus etc. and M0 is not 0. And this is not a real assumption. We could just shift the module to make it true, or we could shift the definitions conversely to make them apply more generally. And then what does the resolution look like? Here's M. There are some generators in degree 0. That's what I just told you. So there's an S to the something or other. Let's call it B0, 0. Plus maybe higher degree generators, S of minus 1. This should be beta, shouldn't it, in my current terminology? Beta 0, 1 plus, etc. Now, what could the syzygies look like? Well, of course, there can't be any generators in degree less than 0, because they would have no place to map. Remember, the maps and resolutions, as I'm writing them, are all homogeneous. So they have to take elements of the same degree. And if I'm writing down a minimal resolution, which is what I want to do, then they can't take any generators to 0. So there is nothing here in degree less than 0. So no generators here can have degree less than 0. But they can't even have degree 0. Because if a generator here had degree 0, then it would go to the degree 0 part of this module And any generator of this free module in degree 0 is a minimal generator. So that would say that that minimal generator went to 0 here, and I could have generated m by fewer things. So this syzygy starts in degree 1, S beta 1, 1 of minus 1 plus more. Of course, there might not be any relations of degree 1, but there might be. So this is the kind of possibility. And then the next one similarly will start in degree 2. So that's the picture of the resolution. Now, the same argument that I just made tells us a little more. It'll tell us, for example, that all those generators of the S beta 1, 1 of minus 1 have to map exclusively into the S beta 0, 0. They can't map into this factor, because if they did, they would kill off one of the generators. And they certainly can't map into any other factor, because there just aren't any non-zero elements there. So this piece that I've written down explicitly on the top is actually a subcomplex. A linear strand is by definition that subcomplex, S beta 0, 0, S beta 1, 1 of minus 1, etc., and is a subcomplex. Now, once you have a subcomplex, which is a direct sum-end module by module, then you could factor it out. You'd get a new free complex, and again, it would have a linear strand. You could factor that out and get a new one. So, in some sense, every free resolution is made up as an extension of these linear complexes. So this is what I mean by a linear complex. So I'll take S, maybe with some twist, but let's start with twist 0 to the A0 S of minus 1 to the A1, and so on, and then maybe I'll twist this whole thing by D. I call this linear because the matrices here are matrices of linear forms. Here are all generators of degree 1, so they have to go to degree 1 things times the generators here. In other words, we have a matrix of linear forms here. So this is a linear complex in that sense. And what we just proved, or what I asserted, which is pretty trivial to prove, is that every minimal free resolution has a filtration by these linear complexes. Now, a lot of the recent work on syzygies has been focused on the question of what these linear complexes look like. They're somehow the easiest piece to get a hold of, and they seem to contain interesting information, too. So why not think about them first? On the other hand, our ignorance is very great, and the main topic that I'll talk about in the next lecture will be how long the linear strand can be. So the analog of the projective dimension, but where you just look at the linear part, you might call it the linear projective dimension of this module. We don't have any theorem like the Auslander-Buchsbaum theorem yet.
Filtration where the factors are linear complex?
The quotients, right. The successive quotients are... no, then the subcomplexes are not linear complexes, but the successive quotients. Yeah. Right. So that's going to be my theme. Let's look at one example just to see that there might be something geometric there. There are quite deep examples, and the main conjectures, the most famous conjectures in this area, Green's conjectures about the form of the resolution of canonical curves, or the Green-Lazarsfeld conjectures about curves of high degree, involve very subtle geometric invariants that can be read from these linear strands, or conjecturally can be read from the linear strands. I don't really have time to develop the background to have you appreciate those as much as I would like you to. So you have to read my book if you want to do that. But instead, let's talk about what is actually a rather more trivial example, but at least it's easy to see quickly, and that's this one. So what is it that's interesting geometrically about the points in this example? Where are the points anyway? Here's one of the points, and the others are these 8. So there are 9 points there, and there's one that just sticks out, right? It really sticks out in a strong sense if you begin to move this configuration around. Let the equations vary flatly and nicely, keeping the resolution the same. Then these 8 points will be permuted by monodromy as according to the symmetric group, whereas this one will stay stuck where it is. So this one is really a distinguished point in this configuration. And that's somehow the most obvious geometric feature. What if we look at the linear strand of the resolution of the ideal here? What does it look like? Well, of course, it's all twisted in the wrong degree. So we have to first twist the ideal by 3 to get a generator in degree 0. But ignoring that trivial problem for a moment, we could write down the linear strand. So, example continued. The resolution of the ideal twisted by 3 for the 9 points looks something like this. I have S2, S squared plus S of minus 1. And then S of minus 1 plus S of minus 3, I guess. And if you look where the maps could possibly go, they go like that. In fact, it's easy to write down this matrix explicitly. The first column has to go with linear forms to these two, so we have L1, L2. Those are the equations of those two lines. And then has to go by 0 to this, otherwise we'd kill off this minimal generator. 0. And the second generator goes to 2 cubic forms, F1, F2, and then a quadratic form, Q. And you can, if you, again, remember the lecture of Jessica's that you may or may not have been to, you know that this determinant is the quartic, which is pictured over there, whereas the 2 cubics are the union of the lines L1, L2, or L2 equals 0 with the conic Q equals 0. So we're seeing L1 and L2. Now what's the linear strand of this? Well, it's just this piece. And the matrix here, the linear matrix, is just L1, L2. So you see before you the ideal of that isolated point. The linear strand has just picked out for us that most interesting piece of the geometry. Right, so this is a very simple but at least transparent example of that phenomenon. Right. All right. Now, the first question you might ask is, how special are the linear strands of resolutions? What is it that distinguishes them among linear complexes? Certainly not exact, right? This complex has lots of homology. Of course, the homology is somehow all in higher degree. That's one answer. right? The homology of this complex is corrected. It's made into a resolution by adding stuff of higher degree. So that's a kind of answer to the question. But there's another answer which has proved very powerful, has begun a tremendous tidal wave of mathematics that now points in a different direction largely, and which I want to explain. Linear complexes are the same thing as modules over an exterior algebra, the Koszul dual of the polynomial ring. And at one level, this grows into the Bernstein-Gelfand-Gelfand correspondence, which asserts an equivalence of derived categories, whatever that means, between modules over the polynomial ring and modules over the exterior algebra. And it now turns out that such derived equivalences appear in particle physics and in birational geometry of higher dimensional varieties and all over the place. Don't worry, I'm not going to go down any of those roads, and I'm not going to talk about derived equivalences at all. But this was the first example, and it grows out of the very simple construction that I'm going to show you in the next hour. So thanks very much, and I think I'll stop there.